Hi students, this is Ms. Oberly with lesson 2.5, postulates and paragraph proofs. And just a heads up, for this postulates part, you will need that postulates packet that you received today in class. Today, you should be able to identify and use basic postulates about points, lines, and planes, and also to write some proofs. So, heads up, fair warning, you are going to do a little bit of writing when you copy these postulates down, but you'll just copy them down once and you will use them all year. So, here we go. First of all, you might be wondering, what the heck is a postulate? And a postulate, or an axiom, is just a fancy word that describes a statement that is accepted as true without proof. So our first postulate is the fancy name 2-1. So where we are naming the postulate, you can just write 2-1. In words, that is, through any 2 points, there is exactly one line. Our definition, so through any 2 points, there's exactly one line. And where it says example or picture, you can quickly jot this picture down. Line N is the only line through the points P and R. All right, 2-2. Through any 3 non-collinear points, there is exactly one plane. So this is postulate 2-2. These are the words or the definition that describes postulate 2-2, and this is your picture. A picture is fine. You can add these words if you're feeling like it would help you. All right, the fancy name for postulate next is 2-3. So that's what it's called, postulate 2-3, and the definition is a line contains at least 2 points. You could draw this picture, or you could add those words. Line N contains point P, Q, and R. And our next postulate is the fancy postulate 2-4, which just says a plane contains at least 3 non-collinear points, and this picture is fine, or you could write the words plane K contains non-collinear points L, B, C, and E. And 2-5, we're about halfway done at this point. Postulate 2-5 is if 2 points lie in a plane, then the entire line containing those points lies in that plane. So if 2 points lie in a plane, then the entire line that contains those points lies in that plane. The picture is fine. You could add the words if you want. All right, a few more. Thanks for hanging in here. Our next fancy name here is postulate 2-6, which by definition is if 2 lines intersect, then their intersection is exactly 1 point. So you could draw this picture. The intersection is exactly 1 point. And 2-7, we have 2 more to go, I think, is if 2 planes intersect, then their intersection is a line. This picture is fine, or you could add the words. And our last big postulate, theorem, or formula, this one happens to be theorem 2.1, just says if M is the midpoint of AB, then the line segment AM is, and we read this as the word congruent, which just means equal to when we're talking about measurement. So is congruent to BM. And that's something, again, that we probably know already, but these postulates or theorems now we can take as fact. All right, example 1, there's 3 examples today, asks us to explain how the picture illustrates that each statement is true. So first explain it, then state the postulate that can be used to show each statement is true. Line M contains points F and G, so let's find line M. Here's M. It contains points F and G. Point E can also be on line M. So let's think back to our postulates, pause the video here for a moment, and think, what postulate talks about that? All right, when you're ready, go ahead and play it. So the edge of the building is a straight line, this line M. Points E, F, and G lie along this line. So they lie along line M. Postulate 2.3, if that's what you were thinking, you were right, states that a line contains at least 2 points, which means it could be 3 points, and that shows that this is true. So remember 2.3, our fancy name here? at least 2 points, that is what shows this is true. All right, let's quiz yourself for one more. Lines S and T intersect at point D. So where's point D here? Here's lines S and T. Pause the video, look back and see if you can figure out which postulate or theorem talks about this. All right, the lattice on the window of the building forms intersecting lines. Lines S and T of this lattice intersect at only one location, point D. That's postulate 2.6. So if you thought postulate 2.6 was the one, you were right. Example 2, determine whether each statement is always, sometimes, or never true. Explain your reasoning. If two coplanar lines intersect, then the point of intersection lies in the same plane as the two lines. So is this always, sometimes, or never true? If two coplanar lines intersect, so they're on the same plane, they intersect, then the point of intersection lies in the same plane. Do we have a postulate about that? Let's look back. If two planes intersect, then their intersection is on that line. Do we have anything about two coplanar lines? What do you think? Does that help us? Well, let's find out. 2, 5. So 2, 5 says if 2 points lie in a plane, then the entire line containing those points also lies on the plane. So in this case, 2, 5 tells us that it's always true, because if 2 points lie in a plane, then the entire line containing those points also lies in the plane. So since both points lie in the plane, any point on those lines, including their point of intersection, always lies on the plane. And part B says 4 points are non-collinear. So let's look back at our postulates. A line contains at least 2 points. So what do we know about 4 points? Well, is that always going to be true? No, sometimes. Postulate 2, 3 states that a line contains at least 2 points. This means a line can contain 2 or more points. So 4 points can be non-collinear, like A, E, C, and D. This E is non-collinear. All right. And lastly, the proof process is something we're going to talk through really quickly. It's a step-by-step process that we will practice in class tomorrow. Step 1 is to list the given information. So I would just say list what's given. The key thing here is given. You don't need to write all of this down. Drawing a diagram also really helps. Step 2, state the theorem or conjecture to be proven. So what are you trying to prove? Step 3, create a deduction argument, and we know what that is from lesson 2-3. By forming a logical chain of statements linking the given to what you are trying to prove. Step 4, justify each statement with a reason. So you got to give a reason for each statement. So give a statement and then why. And this is where we're going to include those properties, postulates, and theorems. And lastly, state what it is that you have proven. So what's your conclusion? What did you just prove? And you should always know where you're going first. So I always like to even kind of write down, this is where I want to end. All right, our last example is we're going to try this. Given that M is the midpoint of XY, write a paragraph proof to show that XM is congruent to MY. So steps 1 and 2, remember, were to list the given information, draw a picture, and then state where you're going. So we know that this is what is given. This is what we're trying to prove. This is the end. So this is where we start. And this is where we want to end. And would you be able to draw a picture for that? Give it a shot. So that's what we're given. We just copy it down. That's what we're trying to prove. And here's a picture where M is the midpoint. All right, step 3 says to create an argument by formal or logical chain of statements linking the given to what you're trying to prove. So could you look at our theorems and come up with any of that? Pause the video for a minute, take a look. All right, so if M is the midpoint of XY, Then, so we always like to start with what's given. That's a good place to start. Then, from the definition of the midpoint of a segment, we know that xm equals my. We know that they are equal to each other. This means that line segment xm and line segment my have the same measure. By the definition of congruence, if two segments have the same measure, they are congruent. Oops. Therefore, and our final statement is to write down what we're trying to prove. Our end, xm is congruent to my. So this may seem kind of like, ooh, I totally knew what that was. But this is really what a proof is. Not too difficult, right?